Okay, so last class we talked about we can define a particular plane this way. You get a point on a plane and you get any two independent vectors, meaning they're not dependent on each other, they're not parallel to each other. Then starting from here and getting some combination of vectors of these two vectors, I can generate any point I want on this plane. Okay, that was the idea. Okay. Now there's another way to express this plane rather than a point and two vectors. So right now we have this, point. Let's say just an example, 1, 2, -1, s, 0, 1, 5, plus t, 2, -1, let's say 7. Okay, so that was the equation. It looked very complicated. It's very long and cumbersome. Here's how we represent it instead. Visually, we can represent this plane by taking this point, instead of using two vectors, just using one vector. That one vector being perpendicular to both of these vectors, or perpendicular to, in fact, any vector, right? Any vector on this plane. Okay. Then we can say what a particular point is on this plane, provided that, let's say, from the see the foot of the again, we call this the normal vector, normal to the plane this time. Right? If this vector right here is perpendicular to this normal vector, then it's on the plane. Right? So if I define a plane using this normal, do you guys agree? Given that I have this point, if I give you a point here, oh, is that point on this plane? You just do this. You draw, right? You draw a vector from the foot of the normal to this point and see if that vector is perpendicular to this one. If it is, then it's on the plane. Okay? Let's say in general, the vector, this has a coordinate of A, B, C, okay? Okay, and let's say this point is X, Y, Z. I use the letter X, Y, Z for, you can vary. You can plug in whatever you want, X, Y, Z. Okay, let's call this point at the foot X0, Y0, Z0, meaning it's some fixed point at the bottom of the normal. So what I just described, how do you check if this point X, Y, Z is on the plane? Here's how you do it. You first find this vector, let's call that vector U, and U will be the following: X minus X0, Y minus Y0, Z minus Z0. We know the U dot with the normal vector, it's going to be 0 because they're perpendicular. If this is perpendicular, then we say X, Y, Z is a point on the plane. Okay. Okay, so let's write that out. N is A, B, C. Dot product, you get the following: A, B, and C. Okay, so distribution, you get AX, BY plus CZ. I'm doing this first. I'm just doing the distribution of this, this, and that first. And then I'm going to have a minus of AX0, a minus of BY0, and minus of CZ0. Okay. This is a constant, agreed? It's a constant. So I'm going to call this, all of this, D. Doesn't this look like the equation of a line? The only extra thing that we have here is a z. if we're missing z, so compare with, right, ax plus by, right, plus c is equal to 0. This was a two-dimensional line with slope of minus a over b, right? Meaning a, okay, so slope of b over a, what is that? That's actually the normal, right? We talked about this. Look here, same pattern. The normal information is the coefficients of x, y, z. Okay. So, two-dimensional line, we add an extra dimension, we get a plane. We don't get a line, we get a plane. Okay, so let's do this process on this. Now, I'm not going to do the whole process. I just discovered that my equation will look like this: ax plus by plus cz plus d. And ABC is a normal of these two vectors. Okay, so I'm going to take 0, 1, 5, and 2, negative 1, 7, and I'm going to do a cross product. Okay, so this is for the vector, normal vector. Alright, so let's do this. And you cross this one out, you get 7 plus 5. Cross that one out, 10. Cross that one out, and you get minus 2. Therefore, the normal vector is 12, 10, negative 2. And we can also just use 6, 5, negative 1. That's a normal vector. So, the scalar equation of the plane, this plane here, starts like this: 6x plus 5y minus z plus d is equal to 0. Now, do you guys follow up to there? Okay, so to find d, we know that this point, 1, 2, negative 1 is in this plane. So we plug it in. 1, 2, negative 1. So d is going to equal to minus 6, minus 10, right, minus 6, minus 10, and minus 1. So d is equal to minus 17. Therefore, the equation of the plane we're looking for, the scalar equation, is this. Okay, that's another way of writing equation of a plane over this one here.